Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In this session, we are going to go over how to find the powers and the roots of complex numbers. We had a session on complex numbers before, but I want to go a step further. So just to refresh your memory and remind you of what we did, we always say that if I can draw a unit circle in which we are going to say that the horizontal axis is the real one and the vertical axis is the imaginary one. So now any any radius that you draw at an angle theta, for example, can be represented as follows. This portion, which is, notice the radius is 1, so 1 cosine cos theta is the real portion, and the vertical is sine theta. So sine theta I, because that's the imaginary portion. So now any complex number that I can represent. In fact, I showed you how e to the I theta is cos theta plus I sine theta. We did that, remember, when we expanded the sine and the cosine, and then we added them and multiplied the cos by I, and we ended up with e to the I theta. You can review that if you want. The session is found on the channel. So we said, uh, of course, this has r equals 1. R is the modulus or the length, so to speak, the radius of that circle. So r times e to the I theta. And then if you remember Euler's formula, we could write this as r times cos theta exactly plus I sine theta, right? Sometimes as a shorthand, instead of writing the whole thing, we say the c out of the cos, and then I imaginary, and then S for the sine theta. So R times cis theta has the same meaning. And again, if you remember, we said, okay, so if we take theta equals pi, I would say R here is 1, so e to the I pi equals 1 cos pi plus I sine pi. But sine pi is 0, and cos pi is -1, so you get e to the I pi equals -1. Yeah, of course it is -1, which means e to the pi over 2 is I, right? You can see right away now what you can do. E to the 3 pi over 2 would be -I, and 3 to the 2 pi I is 1. Interesting, right? This is Euler's formula. Then came the Moivre. The Moivre said, if I want to raise z to any power n, it becomes, well, this is a number, so r to the n, times e to the I theta, everything to the n. And then he said, well, I'm sorry, e to the I theta to the n. We know that x to the a raised to the b is the same as x to the ab, so that power becomes a multiplier, which makes it so easy. I can rewrite this as e to the I n theta. So between these two giant mathematicians, we have a very simple way of raising any complex number to any power we want. So let's take an example. Let's start by saying, suppose I have a complex number z, which is 2 minus 2 root 3 I, for example. and I want to raise it to the third power. How do I do that? Well, one way is to multiply it over, so square this number and then multiply it by, it's a lengthy way. An easier way is to find the modulus of z, which, well, let's say z is that, and then we want to find z cube. Okay, I'm sorry, I did the cube quickly. Okay, so the magnitude of that, notice if I can take 2 out, that becomes 2 times 1 minus root 3i. So that becomes 2. And to find the length of a vector, well, that's basically the same as what we did with vectors. So we get the norm of the vector. If you remember, you take the square root of the real portion square plus, not minus. Never subtract. It's a huge mistake. Okay, you always add the negative root 3 quantity square. So you get 2 times the square root of 1 plus 3 equals 2 times 2 equals 4. So the length of this is 4. Okay, that's the first thing you find, the modulus. Then you find, so this is the modulus, which is really the length. And then you find the argument, which is the angle, theta. So theta from the figure is so easy because you know the opposite, you know the adjacent. So it's arctan opposite, which is the imaginary, over the adjacent, which is the real. So it's a tan, or same thing as arctan, is 10 to the negative 1, but most mathematicians prefer that you write it arctan. So I apologize for the negative 1. Arctan of the imaginary portion over the real portion. So what is theta? I know that arctan root 3 is pi over 3, 60 degrees, right? But is it 60? Be careful. The imaginary portion is negative, meaning I am below the horizon in the third or fourth quadrant. The real portion is positive, so the x is positive, the y is negative, I am here. So really, this angle is pi over 3. This is pi over 3. But we always measure the angle from the 0 counterclockwise. So this thing is 2 pi minus pi over 3. 2 pi is 6 pi over 3. Minus pi over 3, it's 5 pi over 3. Okay, so now I would say if I want to raise this to the third power, we said cube, so z cube becomes 4 cube, which is 64, times e to the I. And if I multiply that by 3, notice cube, you multiply the angle and you cube the modulus. But you triple the argument. So times 3 is 5 pi. I know that every 2 pi, I go back to where I start. So I can subtract multiples of 2 pi. In fact, I can subtract 4 pi. And I get 64 e to the I pi, which we said it's negative 1. So I get negative 64. Wow, I started with a complex number. I kept multiplying it by itself. And I ended up with a real number. Yeah, but you did the same thing here, right? So let's see. Let's see if we say take 2 minus 2 square root of 3i and raise it to the third power. Let's see what we get. We got negative 64. Interesting. So this is the same as negative 4 cubed, right? Okay, keep that in mind. Let's take another example. This time, let's make a root. So let's say I want to take, What do you think? We can make up some numbers. Let's say z equals 3 times times I really don't care. I don't have something in mind. Well, we can do 3 and 4, so we get an argument of 5. It would be easy, but or 5 and 12 and get 13, whatever. But let's make let's make something for which we know the angle, so it would be easier, you know? It doesn't have to be. Okay, in order to prove it to you, I'm not going to use that. No, I'm going to say 1 plus 2i, for example. That's it. That's enough. Okay? And they ask you to find, say, the cube root of z. So we did a power, let's do a root. Okay. The first thing I do, I find the modulus of z. Of course, the 3 is a constant, so you take it out times the square root of 1 square plus 2 square. So it's 3 root 5, which we can take cube that or take the cube root of that later. And then I find the angle theta. It's arctan 2. Oh, again, I wrote arctan to the, I'm sorry, atan 2. Alrighty, so now you can write this as the modulus 3 root 5 cis atan 2. So to take z to the 1/3, you will get 3 root 5, the cube root of that, or to the 1/3, times e to the I arctan of 2 over 3. It's not arctan 2/3, by the way. We are not dividing the 2. We are dividing the angle that we don't know. It's more than 45, more than pi over 4, because arctan of 1 is pi over 4. And it's even more than pi over 3, because arctan of pi over 3 is root 3, which is 1.732. So 2 is more than that. But we are going to divide it by 3. Here you have to be careful. I will tell you why. But let's do this first. So if I use my calculator and get 3 square root of 5, oops, I should have put that between parentheses. Raised to the power of 1/3, I will get 1.88 something, okay? And then I will get theta, which is arctan 2 divided by 3. And this is the angle. So so uh so this is the angle, right? So how do I write this? Well, basically I can take the 3 root 5 to the 1/3 and multiply it by cosine of this angle, close, plus I sine of that angle, close, close. So I get 1.759 plus 0.6803 I is the answer. I will go back and talk about that, but this is, let's take this number. So let me first of all open a parenthesis and then take this number and cube it. What do I get? I get 3 plus 6i. 3 plus 6i. Someone would say, But when you take the cube root, shouldn't you end up with three values? Yeah, absolutely. So why did you show us only one? I said this is the first one. Notice that when I get an angle like arctan 2, if I add 2 pi to it, I will go back to the same angle, right? So this can be arctan 2 plus 2 pi, the whole divided by 3. Let's see what we get if we do that. If I say arctan 2 plus 2 pi, close the parentheses, over 3, I will get an angle here of 2.463. Now, let's repeat that using this angle. So we are going to say 3 root 5, which we had before, this number, multiplied by cos of this angle. Oops, no, oh yeah, it's correct. Okay. Cos of this angle plus I sine of this angle. I will get negative 1.469 plus 1 point, I hope I did it correctly. So again, I'm going to go down, take this number, close it, and raise it to the power of 3. Yeah, I get 2.9999, which is 3, plus 5.999, which is 6i. Same thing. And then you would say, oh, so the third one, I'm going to add 4 pi. Yes, absolutely. So I will go, again, we can rewrite it instead of keep going up. 3 square root of 5 to the 1/3. That was this modulus. And then we are going to multiply it by cos. Oh, let's find the angle first. Yes. So the angle is arctan 2 plus 4 pi now, right? Because we added 2 pi, you add another 2 pi. If you add the third 2 pi and then divide by 3, you get back to the first one. So you don't have more than 3, right? So let's get this angle divided by 3. So this is the new angle. Okay, so I'm going finally to say this times cos of this angle plus I sine of this angle. Did I open parentheses? I think I did. Okay, so I get the third root would be negative 0.29 minus 1. This doesn't make sense. Is it? Does it? Let me see. 8.63. So let's see if I hope I didn't do any error. No, correct. 3 plus 6i again. So you see, it's so interesting, right? You can find any roots, even the 10 roots of a complex numbers by keep adding 2 pi and divide by 10 or whatever you have or whatever value you were asked to do. Now, I hope this was easy for you. I'm going to take another example that may look crazy, right? You might have seen this online. I mean, there are people who show this stuff. Suppose you want to evaluate what is I to the power of I. Say, what? How even do I think about that? Every time you have something to the power of I, use your common sense and say, I learn in math that I can take e to the power of natural log or natural log of e. They are inverse functions. They cancel each other. So I can rewrite this as e to the natural log of I to the I. Right? I didn't do anything. I just multiply e to the natural log. Now I know that if I have natural log of something to a power, the power becomes a multiplier. So I can rewrite this as e to the I natural log of I. Now it looks like e to the I theta. But I'm not going to use the cis. I'm going to say, do you remember here what we did? Do you remember that I gave you this equation? And it wasn't really an equation. You could have found it yourself by saying, okay, I, the angle is pi over 2. So e to the I pi over 2 is I. This is extremely important because if I take the natural log of both sides, yes, math whiz would say, oh, the natural log and the e are inverse functions, so I get I pi over 2. So the natural log of I is pi over 2i. Natural log of I is pi over 2 times I. But I times I is -1, so you get e to the negative pi over 2. I to the I is e to the negative pi over 2. Again, imaginary number raised to an imaginary power ends up giving you e to the negative pi over 2.208, a real number. And to finish it up, I will show you what about the ith root of I. This is an easy one. You will see in a second. I to the ith root of an I is I to the 1 over I, right? What is I to the 1 over I? Let's see. I'm going to say it's e to the natural log of I to the 1 over I equals e to the 1 over I times natural log of I. But we already said that the natural log of I is pi over 2i. So it's e to the 1 over I pi over 2i. The I and the I cancel and you get e to the pi over 2, which is the reciprocal of that. Second, e to the power of pi over 2 is 4.81. And until our next session, I wish you all a best day, or all the best in the world. I'm so excited that we covered this. I think we needed to simplify the roots and the powers of complex numbers, and I hope you got this one down. It became history now. You can do all the problems very easily. I wish you all the best again, and if you have any comment, please leave it in the comment section, and I will try to get back to you as soon as I can. Thank you very much for watching. Have a great day.